Hello everyone, this is the EC 528 Cloud Computing Research Paper presentation. The research paper I have chosen is Dynamic Resource Allocation using Virtual Machines for Cloud Computing Environment. What this paper talks about is every virtual machine needs to be mapped to a physical machine. VMMs or hypervisors are the technology that allow us to map virtual machines to physical machines. The goal of this paper is to achieve this mapping in such a way that no physical machine is overloaded with utilization or underutilized. The paper talks about designing and implementing a resource allocation system that can avoid the overload in the system and minimize the skewness and balance the resources. When we talk about skewness, we are referring to the utilization of compute, memory, storage, all kinds of resources equally without any unevenness. And we're also trying to predict the future usage of a virtual machine without having to interrupt its isolation and security. So overall, we are trying to design a system that can overload the that can avoid the resource overload, minimize the skewness and balance the resources, and also predict the future usage of virtual machines without looking into the virtual machines. Now we're going to look at the system design. Each physical machine runs a local node manager that collects the usage of statistics of resources and sends it to the Azure central controller. The VM scheduler itself has three parts: predictor that can predict the future resource requirements of a virtual machine, hotspot solver to detect a physical machine overload with resource usage or exceeding the hotspot threshold. Cold spot solver checks for physical machines which are underutilized and can be turned off to save the energy. Algorithm also predicts future resource utilization, future resource needs, with the formula being shown on the screen, where E of t is the estimated load time and observed load time is O of t. Predict the future behavior, we cannot pull the statistics from the virtual machines directly due to the isolation and security. Hence, we rely on external behavior of virtual machines to predict its further future usage. We will see further into the presentation why future load prediction is essential. And also this method is called as fast up and slow down algorithm. We have multiple resources on one physical machine, such as memory, compute, and storage. Skewness is the measure of unevenness of utilization of these multiple resources on one physical machine. Not all resources are equally utilized. Hence, the algorithm also has to ensure that virtual machines with different types of workloads are combined on one physical machine in order to minimize this skewness. The algorithm also checks for hotspots and cold spots frequently, hotspots being the physical machines whose resources are overutilized, and cold spots being the machines which are underutilized. For hotspots, the virtual machine is moved to another physical machine in order to reduce the load on that physical machine. Green computing is the term used for when the resource utilization of the physical machine is so low that it can be turned off to save power. The green computing algorithm is evoked when the overall utilization of all the physical servers is below the green computing threshold. The solution to a cold spot is migrating the virtual machine to another physical machine and turn off this machine in order to save power. So the graph that you're seeing here is a simulation of the algorithm for the given amount of time and the number of active physical machines. So for the same amount of CPU load, when we change the threshold of the algorithm, we can see that the number of physical machines that are active and turned on at that given amount of time also varies. The next simulation that we're seeing is for the scalability of the algorithm. The scalability of the algorithm refers to how many virtual machines and how many physical machines are we applying this algorithm on. And as you can see from the graphs, the average decision time increases when the amount of physical and virtual machines increase because the algorithm takes more time to make a decision. And the average number of migrations and the number of migrations per virtual machine also increase as the amount of virtual and physical machines increase. The algorithm still works when the size of the when the number of virtual and physical machines increase. So this algorithm is well scalable for any amount of virtual and physical machines, but it works best when the ratio of virtual machines to physical machines is 10:1 according to the paper. This is a simulation of the effect of load prediction. Like we talked earlier, it is important to determine the load on a given physical machine in future, because if a physical machine is underutilized, it might only be an temporary trend, or it might be experiencing an intermittent underutilization. If we do not know that this is an intermittent underutilization, we might shut down the physical machine and migrate the virtual machines. And again, when the load or the utilization of the resources increase, we might have to boot up the physical machine again and move the virtual machines back to the physical machine. This will cause a lot of migrations. Hence, if we know that there is going to be a future resource utilization on a physical machine, it can reduce the number of migrations, as you can see from the graph. Experiments from the paper to emphasize on the effect of load prediction. The graph that you are seeing is the number of requests of each second for a virtual machine, which is acting as an e-commerce machine. So the traffic is generated from the users who are trying to access the e-commerce website per second. As we can see the trend, there is a burst in between, which is called the heavy load time, where there are a lot of requests being generated, like how you would see in an e-commerce website when there is a flash sale or a deal. That is a momentary period of spike in the number of users, and again there is a dip in the number of users. And you can see that the number of active physical machines also varies when there is a spike in the resource utilization or the number of requests per second. Finally, we talk about the impact of live migrations. To solve the hotspot or the cold spot problem, we are moving a virtual machine from one physical machine to another, which is called as the live migration. And there was an experiment conducted and listed on the paper about the impact of these live migrations on the virtual machine or the requests. And it was observed that there was little to no impact on the live migrations. So, to sum up the entire paper, the paper's attempt or the goal of the paper is to design and implement an algorithm that can handle the cloud resource management in a better way. We have to manage resources in such a way that no physical machine is overloaded or underutilized. And when we refer to skewness, we have to make sure that all the resources are evenly utilized on a system. No system should be overloaded or no system should be underutilized, which is overload avoidance and green computing. So through this algorithm, we are achieving overload avoidance and green computing. We are solving the problem of hotspots or overutilization by migrating the virtual machine from one physical machine to another. And we're solving the green computing problem by shutting down the servers which are underutilized. Through this, we're able to save power and also make sure that no physical machine is overutilized.